Okay, so I'll make a start. It was suggested I give a few talks about things that interest me. None of them are directly related to systemic risk, but they're all related to risk. In a couple of weeks, I'll talk about backtesting, but today I'll talk about something completely different, which is some work I've been doing. It started with a collaboration with Andrew Smith, who's an English actuary, who's full of interesting ideas that he uses in practice, and then continued with the collaboration with Rüdiger Frey, who's one of the co-authors of my book, and then Emanuele Giorgi, who is a PhD student in Lancaster. So what I'm going to talk about is how to construct scenario sets in a way that is related to risk measures, and the motivation will be stress testing. And there's a bit too much here, 63 slides for 1 hour, so I'll do the theory before lunch, and then if you have enough appetite, you can come back after lunch, and I'll try and turn it into something more practical and create some examples and show how you calculate some of these things in particular situations. So, this is what I propose to do. I will motivate this talk by talking a little bit about stress testing and what is required by the regulators. I will then give a result which connects scenario sets to risk measures, which is in fact the basis of everything else that I will do. I'll spend a while talking about the value at risk measure and its relationship to half-space depth, which is a concept in statistics that not many people know about, although it has quite a long history. Do you know about it, Hans? No? Okay. And then I'll move on to other risk measures, expected shortfall and the expectile. Expected shortfall, well known to be coherent. The expectile, quite fashionable at the moment because it combines the properties of coherence with elicitability, but more on that later. There's then a section on VAR superadditivity, because the theory I tell you about is very nice for creating examples of VAR superadditivity. Then the relationship with capital attribution or allocation, upper bounds on VAR, and then sections 6 and 7 I'll do after lunch. How do you compute these things in practice, and what does this have to do with stress testing? So to begin at the beginning with some motivation. So you hear quite a lot about stress tests in the also in the news these days, banks being stress tested. They've been around for a while. They're part of the Basel framework. If you read some of the literature, you'll find that they're mandatory for banks. In particular, banks do them as part of their Pillar 1 risk measurement. So if a bank uses an internal models approach, either an internal model for market risk in the trading book or an internal ratings-based model for credit risk in the banking book, they're also supposed to do stress testing. And then under Pillar 2, which is the supervisory review, they also have to do extensive stress testing. Not only banks, but also insurance companies. So in the Solvency II regulatory framework in Europe, basically the whole framework is designed like a stress test. So insurance companies have to have capital to withstand a 200-year stress event. And a lot of in fact, the methodology that is prescribed in the standard formula approach is basically based on the idea of a stress test. So what is a stress test? So to keep it informal, what the essence of a stress test, the idea is that you subject a portfolio or you subject the whole balance sheet of a bank or an insurance company to a scenario. Things that could happen. Now, generally, this scenario is expressed in terms of financial risk factors, prices and rates. Possibly it is expressed in terms of macroeconomic factors, changes in macroeconomic variables over certain time periods, like changes in GDP, changes in unemployment, etc. The scenarios, they can be historical. It can be something which happened in the past, which is then replayed replayed with the portfolio that you have at this moment in time, or the balance sheet you have at this moment in time. So you can see the effect of a historical crash scenario. When prices did different things, you can test that scenario on your portfolio today. The scenario may be hypothetical. The regulator may just say, well, tell me what happens to your balance sheet if this set of events all happen. So perhaps its prices fall by 30%, there's some shift of 2% in the yield curve, GDP falls, and all kinds of other things go wrong at the same time. So the scenario could be historical, it could have happened, it could be hypothetical, it hasn't happened, but you're asked to think about it. It could be generated in an economic scenario generator. So a lot of the insurance companies, for Solvency II, they either build or buy economic scenario generators from certain vendors. And these are basically just big Monte Carlo models that generate scenarios for changes in the term structure of interest rates, movements of financial markets, movements of volatilities, etc. So those are scenarios, and as I've said, generally expressed in terms of changes in financial risk factors or macroeconomic variables. Now, the Basel Committee says that scenarios should be three things. On the one hand, they should be severe because you are trying to test a balance sheet or a business model under severe situations. They should be plausible because you can always invent a ruin scenario. If you look at a business model of a company, you can probably think of a scenario that will ruin it. But if it's implausible, well, the companies have to live with risk. And the question is it plausible or is it totally implausible? So it should be plausible, but severe. So there's a fundamental tension between scenarios that are both severe, but on the other hand, plausible. And you should be able to interpret them. They should suggest some risk-reducing action. Now, there's another idea which has been introduced by the regulator, that is the reverse stress test. So that is the idea of the scenario that is most likely to cause a business model to fail. So one way of thinking about this is if you look at the set of all ruin scenarios for a particular portfolio, then what is the most likely way that you will be ruined? So that is the idea of the reverse stress test. So now, what am I going to talk about? I'm going to talk about constructing scenario sets, and the notation in mathematics will be relatively simple. For a start, I'm just going to talk in a static distributional model. So there's a random vector x which represents changes in risk factors over a time period. And so these are risk factors that are going to affect a portfolio, whether its value goes up or its value goes down, or a whole balance sheet, whether that goes up in value or down in value. So in other words, factors that will affect the solvency position of a firm. And I will assume that we have a model for X. So through analysis of data, through consultation with experts, we have a model in the form of a multivariate distribution for these risk factors X, or for these changes in risk factors X. And what I will do is I will define measures of plausibility for points, small x, with respect to the distribution of big X. So I want to define measures of plausibility. These measures of plausibility will not be defined in terms of density or likelihood. Even though we sometimes use the word likely, of course it has a precise meaning in statistics in terms of the density. So I will avoid use mostly of the word likely and use the word plausible. And there are different degrees of plausibility. So rather than using likelihood or density, in fact, I'll use concepts of statistical depth. Okay, and basically the idea is depth inside of a distribution, but this depth can be defined with respect to different risk measures. So the best known form of depth is half-space depth, which relates to quantiles. But I will define some other measures of depth as well, which relate to, for example, expected shortfall or the expectile. And then I'll use the depth measure to define scenario sets. So let's call a scenario set, I guess I can use this. Yeah, so let's call a scenario set S. That's my set of plausible scenarios. I want to create a scenario set that is big enough that it contains some scenarios that are also severe. And then I want to use them in the stress testing context. So here are two possible formulations of a stress test. One I would call the ordinary forward stress test. The other I would call the reverse stress test. So once you've defined the set of plausible scenarios, among all scenarios in that set, you might want to find what is the worst, what has the worst possible impact on your portfolio, where the impact is described by a function L. So if you know how scenarios will change, if you're given an X, then you know what it will do to your portfolio. L will be a known function. You know, it will be portfolio weights, it will be valuation formula, Black-Scholes or something else, which reference these risk factors. So this function L, if you like, will embody the idea of market-consistent valuation and revaluation of a portfolio under scenarios. You were going to ask something.
For your vector of risk changes, is it a one-time step? So
yeah, it's one time. It's one time step. You could add time subscripts and turn this into multiple time steps, but I'm not going to do that at all today. We're going to just learn some things in one time step. So that's forward stress testing. Given the scenarios, given your knowledge of the portfolio and the impact of changes in risk factors, what's the worst possible impact? And then what is the scenario that is responsible for the worst impact? What you can, once you've determined the worst scenario, you can look at it. And then the reverse problem is, among all ruin scenarios, among all scenarios that would lead to a loss in value that was ruinously large, what is the most plausible way of being ruined? And I've written two acronyms after these two questions, Leslie and Mallory. This is due to my collaborator, Andrew Smith. He works for Deloitte, actually, so he has to sell things. So he calls the worst possible scenario, he calls it the least solvent likely event. I'm not particularly happy with the naming because, as I've said, I'm not going to use likelihood. I would rather call it the least solvent plausible event, but that doesn't give you such a nice acronym. You can't call it a Leslie. Mallory is the most likely ruin event, but again, I would prefer to call it the most plausible ruin event, because I will avoid the use of likelihood. Okay, so that's the context. Now I'm going to define things and notation and get going. So a lot of this will be well known to you. In the background, there's a probability space, and I'm going to consider a set of random variables, which is a subset of the space of random variables which are almost surely finite. Every random variable L in my set of random variables M will represent a loss. That's why I'm calling it L. A loss incurred on a portfolio or a position over this fixed time interval. So the way I set things up, of course, there are two different ways of setting up these risk measures according to whether you analyze the losses or whether you analyze future values of the portfolio. I will do it here with losses. And so a risk measure, the interpretation is it's a mapping. I'll use the variant rho. It's a mapping rho from this set of random variables into the real numbers. And the interpretation is it's the amount of capital that we need to back a portfolio or a position which has loss L, loss represented by the random variable L. So much of this is well known to all of you. I will remind you of the axioms of coherence. Here they appear with the signs which are necessary for my interpretation of the risk measure. So a risk measure is coherent if it satisfies four properties which are given here: the monotonicity property, the translation invariance, where m is a constant here, subadditivity, and positive homogeneity. I don't think I'll go into that in more detail. I'll take these axioms as things that are pretty well known to a lot of people by now. And of course, you know that not all risk measures are coherent. And to begin with, the Heriot risk measure, although it satisfies monotonicity, translation invariance, and positive homogeneity, it fails to be subadditive in general, but is subadditive in certain situations, and we'll see some of them this morning. Whereas expected shortfall and the expectar, which will be my other examples, they are coherent risk measures. So the next thing I need to define is a linear portfolio set, not because I believe this represents portfolios in the real world, but because this is what I need to get something tractable. So the linear portfolio set, basically I fix an underlying random vector, or the distribution of an underlying random vector for these risk factor changes, and I look at linear combinations. So lambda times x, the scalar product, some lambda I xi, and I can also add or subtract constants. And so that's my linear portfolio set. So just right away at the start, this is not considered a realistic model for real-world portfolio losses. It is just the means by which I can make a connection between. You look like you want to ask something. No, okay. It's just the means by which I establish a connection between risk measures and sets. So it's a choice made out of convenience, but of course for short time horizons and market risk applications, it's quite common that you use a delta approximation as a first order approximation of the loss. The risk measures that I consider will all be translation invariant, and so just a little bit of notation. If I write L lambda, I'm just basically ignoring the constants and considering portfolios given by lambda transpose x. More notation in order to state some results. So having defined this linear portfolio space, I can replace or represent the risk measure by a risk measure function in d-dimensional space. So this talk will be quite geometrical. So we'll be thinking in d-dimensional space. So for any risk measure rho, define a risk measure function in this way. So lambda is a point in d-dimensional space, and r rho of lambda is basically rho of lambda transpose x. So I'll drop the explicit reference to the vector x. The vector x has been fixed at the start. All my risk measures will be translation invariant. So suppose rho is translation invariant, and this positive homogeneity property for the risk measure will be equivalent to positive homogeneity of this function on RD, of the risk measure function on RD. So by that I mean that for positive constants, you have this property. That will be used later on because under this property we can do this. We can use this Euler rule. And when I establish a connection between the sets and capital allocation, we'll need that. Also, assuming translation invariance, subadditivity of the risk measure on this set of portfolio losses is equivalent to subadditivity of the function in d-dimensional space, meaning that for two vectors in RD, we have this.
I'm slightly confused. You said that x was fixed, but you mean the distribution of x is fixed, in which case the risk measure has an expectation somewhere, doesn't it? I mean, you know, you've got real valued functions there I mean, you see what I'm saying? That r of rho is not a random variable, is it? Or is it?
No, it will turn out to be a real number obtained by applying this functional rho to a random variable.
Yeah, that's what I thought. So somewhere buried in there is an expectation, or at least some way to convert a random variable.
Yeah,
There's some
it's buried in rho.
Yeah,
Rho converts a random variable into a real number. And it could be a quantile, could be an expectation, could be an expected shortfall,
Yeah,
etc.
of course, they can
Yeah.
be different measures, yeah, but you want a
Yeah.
number from it.
Lambda is also fixed, that's your portfolio weight.
We're going to consider all kinds of portfolio weights. X is fixed, lambda can change. And so we consider this function of lambda in d-dimensional space.
But lambda
But when it's true that when you come to analyze a particular portfolio, then that relates to a particular lambda. But we will consider all possible weights. The final piece of notation I need before I can get going and create some sets rather, half spaces and hyperplanes. So I'll write a half space in this way, H for half space, Y and U, because it is described, if you like, by a point and by a direction. So Y is a point in RD, U is a direction, exclude the zero direction, and HYU refers to this half space, the closed one, bounded by a plane through the point Y with normal vector U. And I will very often want to refer to the probability of a half space with respect to this random vector X. So basically I mean the probability that X lies in this half space HYU, which is given by this. Okay. The final part of the introduction is to state something, or to state a little result which relates the risk measures to scenario sets. So this result applies to coherent risk measures on this linear portfolio space. So a translation invariant risk measure, rho, on the linear portfolio set M is coherent if and only if you have a representation of this form. If and only if you can write its risk measure function as the supremum of lambda transpose X for X in a set. Okay, and the set S rho is given in this way. Okay, so this probably requires a little bit of thought. Let's maybe start with the set S rho. This set here is basically an intersection of half spaces. So we're looking at the points X, which satisfy this condition, U transpose X less than R, less than the risk measure function for all directions U. Okay? All the points that satisfy this inequality for all directions U. So this is basically an intersection of lots of half spaces. This equation defines a half space. And what I'm saying is that a translation invariant risk measure, it's coherent. That is equivalent to saying its risk measure function can always be written as the supremum of lambda transpose X for points X and S rho. For those who know convex analysis, this is saying if and only if the risk measure function is the support function of a particular convex set. Because this is the intersection of half spaces, which are convex, trivially, then the intersection is also a convex set. So I'm saying that this coherence is equivalent to the risk measure function being a support function of a particular convex set. And the idea in relating risk measures to sets is that we choose S rho as the natural scenario set when we work with the risk measure rho. People who know a lot about risk measures are looking at this and thinking, this is just an application of a deeper result, which is what you get from the general characterization of coherent risk measures if you apply it to the linear portfolio set. I'll come to that in a second. So I'll choose the scenario sets in this way, closed convex set, and so there is a worst case. So if you do fix a lambda, fix a portfolio if you like, fix a lambda, there is a worst case for that lambda, call it X star, which is the one that maximizes lambda transpose X in the scenario set. And what's nice about this scenario is it leads you directly to a loss. It's a scenario that will give you a loss of size rho lambda transpose X. So for example, if rho is the expected shortfall, this is a scenario which will give you a loss at the level of the expected shortfall, say the 90%, 95% expected shortfall. Okay, so that is the worst case in this set.
Can I just
Yeah.
hold you? I'm puzzled. It's probably a stupid question.
Yeah.
But I mean, 2 seems to me to rely on not for all u belonging to RD, but for a finite number, doesn't it? Because I mean, what about u and minus u? Doesn't that mean then, you know, that you've got both inequalities given the, or not? Maybe I can't see it whether it's positive.
Yes, so
I mean, the
the,
point is that that's going to restrict that to an equality, and that's not what you want, really. You want a half space. But if u is a finite number, which will be the case in your scenarios,
actually, no. The scenarios will be the points x rather than the
Right.
directions u. I literally am thinking of all possible directions. I literally am thinking of all possible directions. And just to kind of give you, maybe we're going to do things like this. Or we're going to do things like this and look at all possible directions and create these sets.
I see.
Obviously, I've looked at a finite number of directions here in order to create a picture, but we'll
Sure.
come back to that.
But in theory, it could
Yeah.
be an infinite.
Yeah,
Okay.
literally all
That's
possible
helpful.
directions.
Yeah.
And just note, so as I've said, for those who know more about these things, it is simply just a special case of the characterization of coherent risk measures as generalized scenarios. But
But how do you prove it? Do you go through the general representation or do you directly on
you
your
can do it. You can do it directly. You can do it directly, or you can go through the general representation. And what you see with a little bit of examination is that basically, when you're working on this set of linear portfolios, every probability measure can be identified by the mean vector of x under that measure. So you can represent the set of measures as the set of Dirac measures on this set. And so that's what happens. I refer here to something that appears in the future. So in this form, it's in the second edition of my textbook,
But
which
we are in the future if you look to the watch.
yeah, we're not that far into the future. But I can, if anyone's interested, I can send you the relevant chapter of the book, which.
12 hours. We are here.
Now, just one little note: when equality breaks down, it will break down in this way, that you will have larger than, the risk measure function will be larger than the supreme when it breaks down. You have equality when the risk measure is coherent, but if it's not coherent, this may break down, and then this will be the direction of the inequality. Now you do.
Probably the same construction works if you replace coherent by convex.
Yeah, I was going to ask that too, actually.
Yes.
Should do, I would guess.
No, in the same way.
I'm not going to say with certainty. To be honest, I never checked, but it should be checked. Yeah. Good question. We'll file that under things to be checked. If we do this for the value at risk, you get a lot of insight into what I'm doing. So this notation becomes much more transparent. So let's make this risk measure here. Let us make it value at risk. It is translation invariant. Of course, it's not coherent. So I'm not going to have this equality in general, but I can construct this set. So I'm going to start by looking at the set 2 for value at risk. And I'll call it a quantile set. So rho is var for some alpha bigger than 0.5, could be equal to, but let's say bigger than. Instead of writing this kind of clumsy thing, I'll write q alpha for this risk measure function. Call it a quantile function. So the scenario set takes this form. It's the set of all points such that the dot product is less than the alpha quantile of u transpose big X. And if you like, it's a kind of multivariate analog of the quantile. It's an analog in d-dimensional space of the quantile. I'll write the boundaries of these sets as partial q alpha or delta q alpha. So because var isn't coherent, that equality we had has to break down under certain conditions. So var is not coherent even on this trivial or simple linear portfolio space unless we assume a bit more for certain assumptions about the distribution X, and for certain values of alpha, it is, but in general it isn't. So one example where it does work, if, for example, you assume that X has any elliptical distribution and you take alpha bigger than a half, then the quantile is coherent on linear combinations of elliptical risks. So that would be one situation where we would have equality. There are lots of nice representations for this Q alpha set. So this is a nice one. Equivalently, you can think of it this way. It's the intersection of all half spaces whose probability is at least alpha. Or you can think of it in terms of a quantity that is known as half-space depth. And this is why I use the term depth. So this idea goes back, I think, to the 50s when Chucky invented the idea of depth, and has been looked at by a minority of statisticians ever since. But half-space depth at a point with respect to a distribution of a random vector X is defined in this way. It's the smallest probability of a half space through that point. That is the depth. And when we look at the pictures, the intuition will become very clear. The smallest probability of a half space through that point. Now, in order to say exactly what Q alpha is, let's simplify things a little and assume that X has a density. Then I can say with certainty that another description of Q alpha is that it is the points whose half-space depth exceeds 1 minus alpha. Okay, and informally, if you like, it's points which are at least 1 minus alpha deep into the distribution. And the boundary of this set is called a depth contour, a 1 minus alpha depth contour. I think now that by doing examples, we get the insight we need. So let us start with a distribution which is actually elliptical and take a bivariate student distribution. And so I'm using this representation here. I'm going to draw the intersection of half spaces that have probability at least 95%. So that's what I do. All these red lines divide R2 into 5% and 95%. If we take a line like this, the 95% is on this side and the 5% is on this side, and you take the intersection and you get this white area here. So that's Q 0.95 for a particular student distribution. VAR is coherent, actually for any alpha when you have an elliptical distribution. But if I didn't already know that through other methods of proof, in fact, the mere inspection of this picture is enough to tell me that VAR is coherent, and I'll come back to that. Have a look at this one. My examples are kind of school book examples rather than realistic ones at this point. After lunch, we take more realistic examples. But here, x1 and x2 are two independent standard exponential random variables. So two independent standard exponentials. And I do the same construction, Q 0.95. Obviously, I don't get something which looks like, this looks like an ellipse and is an ellipse. Here I get something else. I get something here. I've written that VAR at the level of 95% is coherent for linear combinations of two independent exponential risks. And I know that from inspection of the picture. Because this is what happens when coherence breaks down. So it's still two independent exponentials, but I change the value of alpha to 75%. And I do the half space construction, so there's always 25% on one side and 75% on the other. And the set here is Q 0.75. But what happens here, somewhere between 95% and 75%, and you can work out exactly where, you get the phenomenon beginning that some of these planes that define the half spaces are no longer supporting. They no longer support the convex set in the middle. And when that happens, then you know that value at risk is not coherent. You know that at the 75% level, value at risk will not be coherent on the linear space of two independent exponential risks. And I can talk about the construction a little bit later on, briefly. Take another example. So instead of just working in 2D, I can show you pictures of 3D. So 3 independent Bernoulli variables. In fact, they are Bernoulli 0.5 variables. So it's 3 coins, if you like, three coins independently tossed. We could generalize this to be 3 bonds with small default probabilities. We could even make them dependent. But basically, the outcomes of these 3 variables, of course, live on the cube with coordinates 0, 0, 0, 0, 0, 1, 0, 1, 1, etc. And if I pick alpha to be bigger than 0.875, the Q alpha set is the cube. It is the cube. So the cube is Q alpha for alpha bigger than 0.875. That is basically 1 minus p cubed, or 7/8, bigger than 7/8. And var would be coherent on the linear space of 3 independent Bernoullis in that case. But if I make alpha equal to 0.875, then I get this diamond or octahedron, which is inside the cube. And I know, from looking at that picture, I know that var at the level of 7/8 is not coherent on this space of 3 Bernoulli risks. And we could generalize that for more. Yeah.
How can you see that by looking at the picture that's not coherent?
Well, it's because for certain directions in 3-dimensional space, there is no supporting plane that contains a probability of 7/8. For example, there's a picture later on, but if you think of a plane which touches this edge here, if you think of a plane which touches this edge and kind of goes straight down here and slices off these 2 points, that is a supporting hyperplane for a certain direction, but its probability is 3/4 rather than 7/8. You can't have a plane that encloses a probability of 7/8 for particular directions that is supporting to the set. We'll come back to that because there's a little section on that, but it is basically the same idea here, because this is a non-supporting plane enclosing a probability of 75%. There is no supporting plane for this direction. The direction is basically normal vector 1, 1. For this direction, there is no supporting plane that encloses a probability of 75%. And for a particular direction here, there is no supporting plane that encloses a probability of 7/8.
From the convexity point of view, all these things have, they have extreme points which are not supporting. And
Yeah.
That's the point.
Yeah.
Really,
Mm-hmm.
I think.
Yeah, so I think for people who are well versed in convex analysis, this is an application of things that are usually quite abstract, but here are more apparent. But I'll come back to this question of subadditivity in a second.
But the interesting point then is that as far as the distribution goes, as soon as you go away from that non-supporting extreme point, you actually get something that's smooth all the way around. Isn't that what happens? That's certainly what happened in your first picture.
It's what happened, yeah, so for discrete distributions, you don't get
No.
smooth all the way around, you
No,
get
no.
edges. And so it's not so much the first when I drew this picture, I thought it's the pointiness, that it's really just the non-supportingness that is the key thing for certain directions, for getting the subadditivity.
But that must have some relationship to the point is that the supporting point of that convex set is non-unique at the point you call it, right? must be
Yes,
some relation there,
yes,
it seems to me.
it's true. It's non-unique.
Yeah.
There are yes,
Yeah.
it's true. It's non-unique at that point here.
Yeah.
There are several directions go through it.
Yeah, that's,
Yeah.
yeah, and that must be related in some way that I don't quite understand. It seems to me, maybe I'm wrong.
We'll go on a little bit because there are some other surprising things that come out of this as
Very
well.
interesting.
So those are some examples. Just to summarize two cases, for elliptical distributions, you have some additivity for the linear portfolios. So that's quite well known. If X is elliptical, doesn't matter what kind of elliptical, if alpha is bigger than 0.5. And you can show quite simply that the scenario set is an ellipse defined by a center, a matrix, and a size, if you like. If you want to see a proof, I give some references at the end, but Rousseau and Rutz showed this about 15 years ago in a paper. And so, in fact, for an elliptical distribution, you actually get the same sets as you do for the contours of equal density. In this case, the sets, the depth sets, I'll call them depth sets, are the same as the contours of equal density. But that is not generally the case. It just happens for these distributions. But otherwise, I don't use density. So everything is analytical. You can work out what is the worst case. It's more interesting to look at the non-elliptical distribution. In general, you have an inequality of this kind, that the alpha quantile function is bigger than the support function of the convex set. So the alpha quantile function is bigger in general. You only have equality of Q alpha subadditive. And what this means, since VAR is not coherent in general, it must always be possible to find portfolio weights such that the value at risk of a certain portfolio is bigger than the worst case in the scenario set. And as I've indicated, the situations where this occurs, they can be identified in the pictures when there is no supporting hyperplane that bounds a half space with probability at least alpha. When you see that in the picture, you know you have a situation where you can pick a direction lambda and you can create an explicit demonstration using that direction of the superadditivity of VAR for non-elliptical distribution. So that again was the picture for the two. When you see this happen, you know that you can create a situation, and the way that you do it don't know that we have white. The way that you do it when you have one of these sets, you have a non-supporting plane like that. All you need to do is find two supporting ones, like that and like that, where this intersection here lies here. So you find two supporting ones, and where the intersection lies completely within the half space defined by this one, and then you can create a situation of superadditivity. Okay, what happens with other risk measures? Enough about VAR for the time being. What happens with other risk measures? I've picked expected shortfall and expectiles because they are coherent. So expected shortfall, let's define it this way. It is the average VAR in this sense, integrating over the confidence level, if you like, and dividing by 1 minus alpha. Well known to be coherent, but of course only defined if X is a finite mean. So I'll make the further assumption that we're in a case where X has a well-defined mean vector. And in this case, rather than write the risk measure function as with this ugly form, I'll just call it S alpha. Now, because expected shortfall is a coherent risk measure, we must have equality here. We must have the representation that the expected shortfall of a portfolio, defined by the direction lambda, is given by the supremum, the worst case of lambda transpose X for scenarios in this set. And the set this time is defined again as the intersection of half spaces, but this time it's not the quantile here, but the expected shortfall. So it's an intersection of half spaces, it's another convex set, but the half spaces are defined by expected shortfall rather than by the quantile. And you can call the set S alpha, you can say that it is the set that contains points whose shortfall depth, if you like, is bigger than 1 minus alpha. It's if you like, it introduces a different depth concept. Maybe I didn't say that at the time, but just to quickly go back to one of these pictures, the idea of a depth set here, Q0.75, basically every point in this boundary can be thought of as being 25% deep into the distribution. That's the kind of rough intuition, that every point is 25% deep into the distribution, at least 25% deep. So when you change to expected shortfall, you can define a different depth measure, which I won't do explicitly, but let us at least have a look at these sets. Firstly, in the case of elliptical distributions, and secondly, in the case of general distributions. If the distribution is elliptical, you just get another ellipse. It's not really interesting. You get another ellipse. The only thing that changes is the size, because the size is now determined by the expected shortfall measure. And you get a worst case again, you get in a simple formula, but again, it's determined by the expected shortfall risk measure. So you get ellipses. But what is interesting is if you pick arbitrary distributions, you're always going to get a set where the hyperplanes are all supporting. Because of the coherence of the risk measure, you're always going to get a set where the hyperplanes are all supporting. So I've taken again the case of two independent exponentials. I've created the set S 65%. I've done this one because the set Q 65% was one where we had non-supporting hyperplanes and where the subadditivity was breaking down. That's not going to happen for a coherent risk measure. So this is a scenario set with the property that for particular directions, these points on the boundary will lead, these scenarios on the boundary will give you a loss that is exactly at the level of the alpha expected shortfall for that portfolio. So you get a nice match between scenarios on the boundary and, or rather these scenarios on the boundary will give you exactly the expected shortfall loss for different values of lambda, the portfolio weights. Expectiles you can also do. Once you've seen this, you realize that you can do it for any risk measure. I have a short digression here about the expectile for those who haven't heard about it. Who's familiar with the expectile? A minority, less than half. So this is all the rage in risk measure circles at the moment, the expectile, because of a concept. Yeah, because of a concept called elicitability. The regulator, the Basel regulator, was coming round to the opinion that they should change to the expected shortfall risk measure, at least for market risk in the trading book. And after years of academic lobbying, that they were working with a badly designed risk measure that was subadditive and that didn't tell you anything about the losses beyond the VAR, they were coming around to the expected shortfall. But a paper by Tillman Gneiting what's the expression, threw the cat among the pigeons. It caused some disturbance because Tillman Gneiting pointed out that expected shortfall is not an elicitable risk measure, and he suggested that that might mean that it could not be adequately back-tested. That is the subject of my next talk. In fact, I don't think that's true. I think it can be back-tested.
Right. There's a paper coming out right now by Shelby.
And Seke, yeah, I've seen this, yeah.
And just a footnote. I mean, this whole rage about elicitability is a concept, is an old concept in robust statistics, well known under the name of an M estimator.
Yes.
And the fact that expected shortfall is not indexed by was already observed a number of years ago by Stefan Weber.
Stefan Weber, he took,
Except that he did not use the term, because
Yeah.
the term was coined later.
yeah, he talked to me about that. And yes, so listable risk measures are risk measures which minimize a certain expected score, a certain expected score. They have that property, and in fact the value at risk is in that sense a listable or an M estimator. It minimizes a particular expected score for a particular score, or it minimizes an expected score for a particular scoring function. That's not true of expected shortfall. It is, however, true of the expectile. It can be written as in fact that's usually how it's, or one of the ways it's defined, as the minimizer of an expected score for a scoring function. The score basically measures the discrepancy between a realized value and a forecast of that value. But that's the subject of another talk. So this is quite fashionable. This is one way of defining the expectile. This will never catch on with the regulator because it's very unintuitive. They're not going to get their minds around this. It's defined implicitly. Y is the alpha expectile of L, or its distribution, if Y satisfies this equation here. These are max functions. Interestingly, the alpha expectile of the distribution FL turns out to be an alpha quantile of another distribution. You can write the alpha expectile of FL as the alpha quantile of what I've called F tilde L. This is a perfectly well-defined distribution function given by this form here. So I'll write E alpha U for the expectile of U transpose X, and it is the same story. Because the expectile is coherent, at least if X has a finite mean and alpha is bigger than 0.5, then the alpha expectile of a loss in this linear portfolio set can be written as the worst case, n plus lambda x for X in a set. And the set is defined in the same way, except that the half spaces are bounded, or the hyperplanes that bound the half spaces are defined in terms of the expectile rather than the value at risk. And once again, you can introduce a notion of expectile depth and say that what the set E alpha is basically all the points which have an expectile depth bigger than 1 minus alpha. So you can do it. So once you see this, you realize you can do it with any coherent risk measure. When X is elliptical, you get another ellipsoid with a different size. But when X isn't elliptical, you get a set with a different shape. If you take the two exponentials, you get different shapes. It's not that you always get the same shape. You change the risk measure, you get different shapes. But with the elliptical distributions, you're always getting an ellipse. Okay, so to finish the last 3 minutes, maybe I'll just say a little bit more about this superadditivity, and then I'll leave Euler allocation and calculation to the second part of the lecture after lunch. But if we want to create superadditivity, we just look at this kind of situation. We try and create a construction like this. So this is the case Q 0.75. If you notice these black lines here, they intersect at a point which is just to the right of this line here. For that reason, to begin with, let's make things a little bit easier. If I take Q 0.65, then those black lines intersect at a point which is to the left of this hyperplane. So I've blown up the corner. And when you see this, you see immediately how superadditivity, an example of superadditivity can be constructed. But maybe if I just walk you through it. So in the previous slide, alpha is 0.65. Pick the direction lambda is 1, 1. So that corresponds to this line here. The normal vector is 1, 1. Okay, so that defines this line. It's the first thing you do. The diagonal line is the line where x1 plus x2 equals the alpha var, or the 0.65 var of x1 plus x2. So that's what that is there. That's the diagonal line, and you can work out what are the points of intersection. Obviously, the points of intersection are 0 alpha var and var alpha 0. The horizontal and vertical lines, however, on the other hand, they are at the value var alpha of x1 or x2, because it's the same exponential distribution. So from that construction, you kind of immediately, let's just jump to point 3, you immediately see that the alpha var of x1 plus x2 exceeds the sum of the alpha vars. So that's a very simple superadditivity example. So in terms of directions, basically I've taken the directions 1, 0 and 0, 1, and I've created something of this form. If we go back to this one, or is it this one, then I have to work just a little bit harder. I have to pick lambdas which aren't unit vectors. I have to pick non-unit vectors to do the same thing. But that's basically what I do in order to create superadditivity. I have written down sort of over elaborately what the construction here is. Q alpha is subadditive if and only if for every possible direction there is a point at the boundary such that the probability of a half space through that point with direction lambda exceeds alpha. You have to be able to find a supporting hyperplane bounding a half space of probability at least alpha in that direction. And if you can't, if you find a lambda, so I've defined a set of directions for which there exists a supporting hyperplane with probability at least alpha. So if you can find a direction lambda which isn't in that set, then this is sort of formally the construction you use to create a superadditive situation. I think you probably have to go through that slowly to see it, but that just formalizes what you do. But the picture tells you what you do.
But what's going on, presumably, is that the distribution itself is sort of strangely shaped at a given level. Isn't that why your supporting hyperplane is away from?
I don't have a good intuition for because the two independent exponentials, that's a very innocuous distribution.
Yeah.
It's a very innocuous distribution, but it's a marvelous example of what can happen.
It seems to be.
Yeah.
It's quite simple.
This is what you were asking. So just to finish this bit here, if I were to lay look at any one of these faces. So don't look at the red plane at the moment. If you look at any of these faces, if I were to lay a plane along a face, it would go through 3 vertices and it would slice off one vertex. That's the point. If I lay a plane along a face, it goes through 3 vertices and it slices off one vertex. But if I lay a plane along an edge in this way, if I lay a plane along an edge as I've done here, kind of just dropped it straight down, then I slice off 2 vertices. And that's the problem. There is not going to be a plane with the same normal vector as this one, which supports the octahedron and only slices off one vertex. So essentially, this is also an illustration of this theorem here, or this little preposition here. You can see geometrically why you're not going to have subadditivity of the quantile risk measure on a space of linear combinations of 3 independent Bernoulli risks when alpha is 7/8 or less. If alpha is bigger than 7/8, you're okay. And you can extend this to dimension D and different, and you can have dependence assumptions for the Bernoullis, etc. And you can change rather than tossing coins, half-half, you can change the probability so that it perhaps represents defaults. And this space, if you like, is in that case the space of linear combinations of bond holdings. Bonds either default or they don't. You have weights lambda. You can short the bonds, so you can have negative weights. So this tells you about subadditivities for long-short portfolios of bonds, if you like.
And what does the picture look like if you take a higher value than the 7/8?
It's the cube. So Q
It just goes to the cube immediately.
just goes to the cube immediately. Then you're in the cube. Then you're the cube.
Oh, okay.
So you drop from the
And then
cube
you
to the
can only-
octahedron.
you can only cut one.
Yeah. I've done the first 5 sections. So after lunch, I should stop because that's what it says on the timetable. After lunch, I'll just say briefly what this has to do with Euler allocation. And then really what I want to do is think about how this is put into practice and think about stress testing. Okay.